Welcome to Yurix AI. This is Lecture 5 of LLMs from Scratch, Zero to Builder. I'm absolutely thrilled you're here with us today because we're looking at what is literally one of the most exciting inflection points in the history of artificial intelligence. Today's main theme? It's all about a really fascinating discovery. That massive scale, and I mean massive, is exactly what unlocked a model's ability to learn brand new tasks with barely any examples at all. So we're going to explore how making these models gigantic fundamentally changed how they learn. Let's get right into it. So for today's explainer, we've got 4 clear objectives. First up, the history of GPT models. Then we'll dive into zero-shot and few-shot learning, followed by autoregressive unsupervised pre-training, and finally, emergent behavior at scale. Okay, let's dive straight into Section 1, the history of GPT models. To really appreciate this breakthrough, we first need to wrap our heads around the sheer scale we're dealing with. So let's define an absolutely crucial term you're going to hear a lot: parameters. Now, if you're just starting your AI journey, think of parameters as the internal variables, or kind of like the brain connections that a model actually learns while it's training. Whenever a model processes or generates language, it's firing off these connections. Basically, the more parameters a model has, the more capacity it has to absorb information and recognize incredibly complex patterns. They are, for sure, the fundamental building blocks of a model's intelligence. Taking a quick look back, the transformer architecture was introduced in 2017, and wow, did that change the game. By 2018, the very first GPT model hit the scene, rocking about 100 million parameters. Then, just a single year later, GPT-2 expanded that to 1.5 billion parameters, which was a huge leap and showed some major improvements. But then, in 2020, researchers at OpenAI dropped the GPT-3 paper, and they took this trend to an absolute extreme, totally paving the way for the horizon of GPT-4 and beyond. They scaled the model up to an astonishing 175 billion parameters. I mean, let that sink in for a second. That was 10 times more than any previous non-sparse language model out there. And the crazy thing is, it wasn't just a bigger number to brag about. This sheer volume of brain connections triggered a fundamental shift in what the model could actually do, and perhaps more importantly, how we interact with it. Which brings us right into Section 2, zero-shot and few-shot learning. Let's explore how this massive 175 billion parameter scale completely changes how we actually teach and direct these models. Traditionally, if you wanted an AI to, say, translate English to French, you had to train it exclusively on translating English to French. But with models this massive, we can use what's called zero-shot learning. This literally means giving the model only a natural language instruction for a task with absolutely zero example demonstrations. You just type, "Hey, translate this to French," and it just does it. It's wild because this is actually the most natural way we humans ask each other for things, right? But sometimes a task is pretty complex, and even us humans need an example to get the hang of it. That is where few-shot learning comes in. This involves providing the model with a few example demonstrations of a task at inference time. Now, the absolute critical part here is that we do this without changing any of its underlying parameters. We are not retraining the model at all. We just fit as many examples as we can right into the model's text context window, usually somewhere between 10 to 100 examples, and then we just ask it to complete the final one. To really cement this idea, think of an everyday card game. Traditional fine-tuning? That's kind of like forcing a friend to sit down and play 10,000 practice hands of a game until they painstakingly memorize every single strategy. I mean, it takes forever, and at the end of the day, they only know how to play that one specific game. Few-shot learning, on the other hand, is like sitting down with a really smart friend, dealing 1 or 2 example hands face up on the table just to show them the rules, and boom, they instantly get it. They just adapt on the fly, right there at runtime. When you compare the two approaches, it's night and day. Traditional fine-tuning requires massively huge data sets and serious computing power for constant gradient updates, all just to adjust the model's weights for one single task. But with zero-shot, one-shot, or few-shot learning, you simply feed the instructions, and a few examples if needed, directly into the text prompt itself. There are 0 gradient updates happening. The model literally just reads the text and predicts the right answer. It's a total game changer. All right, moving on to Section 3, autoregressive unsupervised pre-training. So you might be wondering, how in the world is it possible that a model can learn a brand new task just by reading a few examples in a text prompt? Well, it all comes down to the engine under the hood. The GPT in GPT-3 actually stands for Generative Pre-trained Transformer, and it operates on an autoregressive principle. Let's break down that fancy technical term into a super simple concept. Autoregressive is simply the process where a model generates text sequentially, basically guessing the very next word based on all the previous words it's already seen. That's it. It's essentially a massive, highly complex game of fill in the blank. But to get incredibly good at guessing that next word, the model goes through something called unsupervised pre-training. And this means training the model on a massive, frankly unimaginable corpus of raw internet text. We're talking books, websites, articles, code, the whole shebang. And the crucial part, it does this without relying on explicitly labeled task-specific datasets. I mean, nobody sat down and manually labeled a million sentences as happy or sad for it to learn sentiment. It just absorbed the messy, natural, beautifully chaotic blend of human language straight from the web. What's truly fascinating here is how the simple, repetitive act of guessing the next word literally forces the model to absorb this incredibly broad set of skills. Because it weighs every single token equally and reads a natural mix of languages and subjects, it develops pattern recognition entirely implicitly. Think about it. To accurately guess the next word in a French article, it has to implicitly learn French, right? To guess the next word in a math problem, it has to implicitly learn addition. And it learns all of this implicitly without a single task-specific gradient update. Over months of this unsupervised pre-training, the model is exposed to thousands upon thousands of these implicit sequences. Sometimes it runs into addition problems, sometimes it's doing translations, sometimes it's even doing spelling corrections. Because these little subtasks are embedded completely naturally within its training data, the model develops this kind of inner loop of in-context learning. It essentially learns how to recognize a pattern in a sequence and adapt to it instantly. And this right here is exactly what sets the perfect stage for few-shot learning later on. Which leads us perfectly into our final and arguably most exciting section, Section 4, Emergent Behavior at Scale. The researchers actually put it perfectly in their paper's abstract, and I want to read this quote to really drive home the standout idea of this entire lecture. They wrote, "Here we show that scaling up language models greatly improves task-agnostic few-shot performance. Scale is the secret ingredient here, folks. You could have the exact same underlying architecture, but if it's small, it's going to struggle. Make it massive, though, it unlocks true dynamic adaptability across almost any random task you throw at it." To see this dynamic in action, let's consider a specific task where the model had to remove random symbols from a text. When you test a 1.3 billion parameter model, even if you give it 100 examples to learn from and its context, it totally flatlines near zero accuracy. It just doesn't get it. But the moment you jump up to the 175 billion parameter model, everything changes. As soon as you give that massive model just a few examples, its ability to learn from context steeply separates from the smaller models, rocketing straight up to over 60% accuracy. The sheer scale is literally what made it a rapid learner. Because of this massive scale, the model suddenly displayed emergent behaviors. We're talking about abilities that absolutely nobody explicitly programmed it for. Out of nowhere, just from reading billions of pages of text, this 175 billion parameter model could suddenly perform 3-digit arithmetic. It could unscramble jumbled words. It could even use completely made-up, novel words dynamically in a sentence after seeing them defined just one single time. Oh, and it could generate synthetic news articles so well written that human evaluators could barely distinguish them from actual real journalism. It's mind-blowing. You can even see this incredible emergent spike in complex logic tasks like SAT analogies. You know, that classic test of logical relationships between words. When you track the performance across different model sizes, the accuracy for the largest 175 billion parameter model spikes dramatically upward, hitting around 65% when using few-shot learning. The massive scale allows the model to suddenly just get it, using only a handful of examples in the prompt, totally outperforming all the smaller models that just remain stuck and stagnant. But this incredible capability leaves us with a really profound question, and it's actually one that the researchers themselves highlight as a potential limitation. When we give a model a few-shot prompt, is it genuinely learning entirely new skills from scratch at that exact moment? Or is it just brilliantly recognizing and retrieving patterns it already vaguely saw buried deep in the petabytes of its pre-training data? Are we truly teaching it a new game, or are we just reminding it of a game it already knows? It's a fascinating, almost philosophical question to ponder as we all start building with these powerful tools. So let's do a quick recap of the core takeaways from Lecture 5. First, scaling up parameter size is the exact key that unlocks the magic of few-shot learning. Second, simple autoregressive pre-training, literally just guessing the next word on raw internet text, builds an incredibly broad and deep set of implicit skills. And third, pushing that scale all the way to 175 billion parameters created unprogrammed emergent behaviors that completely changed the landscape of AI forever. Scale, quite simply, changes everything.